Okay, so for this first problem we're going to do, problem number 4, we're going to do a distance rate time problem. So two cars leave a gas station at the same time, one traveling north and the other south. The northbound car travels at 50 miles per hour. After 3 hours, the cars are 345 miles apart. How fast is the southbound car moving? Alright, so there's a way to do distance rate time problems that helps you keep yourself organized. We're going to start out like we always do by defining a variable. So let's say that x equals the speed of the southbound car. Now, the method I was talking about relies on a table. Okay? We're going to have a table for all of the moving objects. They could be planes, they could be trains, they could be cars, they could be runners. So it really doesn't matter what they are, just they're the two actions that are going on. So we're going to have a northbound car and a southbound car. Alright, so we create a table. It's relatively large, gives us room to work. Now, there are going to be 3 columns. I know we call them distance rate time problems, but today we're going to use them as rate time distance. Now, the basic idea is that rate times time equals distance. D equals RT. So whatever we put into these two cells here, the rate and time cells, we are going to multiply to fill out the distance cells. Once we have the distance cells, we will relate those to the problem, and that will give us our solution. So, just pull data out of the problem. The northbound car is traveling at 50 miles per hour. Now this is one sticking point. You have to make sure that your units agree. If you have miles per hour and your time is in minutes, you need to make an adjustment to one or the other. We don't know the speed of the southbound car, but it's our variable. So x is the speed of the southbound car. They're both traveling for the same amount of time, 3 hours. So in this simple problem, we're just going to put 3 in both. But if your variable is ever a unit of time, like in the next problem, what you need to do is think of it like a stopwatch. If I start running, we start the stopwatch. And if you start an hour later than that, then that means that the stopwatch is going to be t minus 1 or x minus 1. If I'm running for 3 hours, you only run for 2 hours. So when we do meet, that's when the stopwatch stops, but it has to have that relative sense to it. Again, I might be overcomplicating it here. Both times are 3 hours. So it makes life a little easier. Now, like I said before, we're going to multiply the rate and time cells. So we get 150. That's the distance traveled by the northbound car. The southbound car is going to be 3x. Now what you do from here varies on the problem. If both cars are traveling the same distance, you can set them equal to each other. If, let's see, what's the case in this one? If they're traveling apart from each other, maybe draw a diagram. That might help. So if they both start in the middle of this diagram, actually this is east-west, not south-north, but if this car travels 150 miles, and the second car travels 3x miles, and we want the whole distance to be 345, then it makes sense that 150 plus 3x equals 345. And that is a very simple equation to solve. Subtract 150. We get 3x equals 195. Divide by 3. And x equals 65 miles per hour, or mph. So that is how fast the southbound car is going. So now you're going to work on the next problem in your packet. I have included a video for its solution. But if you guys feel confident with it, then we can just go to the video for the problem number 6.